So last class, we did some theory stuff. Adjust the margins. We did some theory stuff last class, specifically with looking at big O notation. All right, I wrote down a few things. We covered the idea of what big O notation means, and there was one thing I said, you guys remember this, really important, and that was what big O notation really tells us. So we look at an algorithm and you say, oh, that's an ON algorithm, or oh, that's ON squared. That's great that you know that, but what does that tell you about the algorithm? And specifically, I said that it shows you the relationship between two things. Anybody remember what it shows the relationship between? Yes?
One of them is the input size.
Yes. Input size. How fast the function goes. Good. So it shows the relationship between the input size and the number of times the basic operation runs. Okay, you guys remember that the basic operation of an algorithm is the operation, the line of code, that contributes most to its total runtime. They're basically the most expensive line of code, the one that's run the most often generally. And so as we increase the input size, the number of times that basic operation runs is affected. And the term inside of big O notation tells us how it's affected. So if it's ON, if we increase the input by 10, the number of basic operations increases by 10. If it's ON squared, if we increase the input by 10, we increase the number of basic operations by 10 squared. If it's log n, and we increase the basic operation, we increase the input size by 10, we will increase the number of basic operations by log base 2 of 10. And this will become more evident as we continue to work with this. But that's really important. Knowing big O of an algorithm is great, but you really have to understand what that tells you and how that plays an impact on adjusting the input size. Okay? Questions on that? All right, so now that we have, you got a question? Oh, no. Okay. Now that we got a question, or now we have a basic understanding of big O notation and analyzing algorithms, we are going to move into the process of analyzing, really breaking down non-recursive algorithms. And for the purposes of this class, we're going to separate algorithms into two categories. Non-recursive algorithms and recursive algorithms. And the reason we break them up into those two categories is the method for analyzing them. And when I say analyzing them, what that means is we go from code or pseudocode. We start with code or pseudocode, and we end up with big O notation. Okay, that's the process that we're going to go through. All right. And the reason we separate into non-recursive and recursive is the method for doing that is different between those two. You guys know we could categorize algorithms lots of different ways. We could say there's sorting algorithms and searching algorithms. We could say there's divide and conquer algorithms. We could say that there's random algorithms. There's lots of different things that we could break them up. But for the purposes of this class, we're just going to divide them up into recursive and non-recursive. Raise your hand if you have done recursion before. 2.5, 3.5 people? Okay. Good. You guys typically don't cover recursion until this class. And the reason for that is nothing you have done up until this point has required recursion. Okay, so we will cover all of that in depth later. That'll be its own class. But what we are going to focus on now are non-recursive algorithms. Non-recursive algorithms are ones that use loops, either for loops or while loops. Okay, so we could call these looping algorithms or iterative algorithms. Instead, we call them non-recursive. Okay. Everybody on the same page so far? So we're going to be looking at algorithms that have some sort of loop built into them. And if you look at the goal, we're going to apply the general framework we learned to analyze the time efficiency of non-recursive algorithms. Translated, we are going to look at pseudocode for an algorithm and analyze it, which means break it down, go through a process to determine what the big O notation, or the class that this algorithm belongs to. Okay? So we'll be able to say, okay, that's an ON algorithm, or that's ON squared, or whatever. Make sense? That's what we're going to do today. Let me know if you guys have any questions. All right, so look at this algorithm right here. And this is the first time we've seen this sort of pseudocode. So I want to just walk through how to read it. There are lots of different pseudocode syntax. This is the one that we'll be using this year. It is relatively straightforward. The only thing that's kind of weird, that's not really intuitive, is this symbol right here. The arrow, it means equals. It's the equivalent of a single equal sign, which you guys know is the assignment operator. So you read this, A at 0 is assigned to max value, or max value equals A at 0. Yes, sir?
Why don't we just use an equal sign?
That's a good question. Yes?
I think it's because when you're assigning something, it goes from the right to the left.
Correct. You're absolutely right, and when you think about it that way, the arrow totally makes sense. Why we don't just use the equal sign, I don't know. People who make a lot more money than I do decided. So we'll go with that. Yes?
Is it so that you don't get confused with equals as a comparison versus assign?
Yes. Why they don't just use two, like, we can talk about this all day. Instead of a double equal sign comparison operator, they use a single equal sign. So why they don't just use a double? Anyways, everything else should be relatively straightforward. This is our assignment operator. Substitute single equal sign for this. And the only other thing I want to point out is when you look at a for loop header, for I equals 1, 2, and minus 1. When it says 2, this means including this number. So if there are 10 values in this array, we know that's index 0 to 9. So there's a total of 10 numbers, total of 10 indices in the array. And so when this says 2 and minus 1, that means start at 1 and go all the way to index 9, and then stop. This is the equivalent of a for loop that looks like this. If we were to code this for int, and they don't put the data type because it's pseudocode. I equals 1. We go to I is less than n minus, it should be less than n, sorry. I plus plus. Okay? So I is less than n is the same thing as saying I is less than or equal to n minus 1. Typically speaking, you don't see this. It's not that it's wrong, but when you are coding for loops, you typically don't see the equal to. They just use the less than. Again, it's not that this is wrong, but this is what you see more often. And the only difference between this and this is what? In terms of typing this and this, what's the difference? It runs the same.
It just includes one more term.
Or keystrokes. What's easier for the computer to run?
The one on the top.
This one. Because this one has to check not only less than, but also equal to, and it also has to perform the math operation of subtracting 1 from n. Granted, negligible stuff, but if these are both equivalent, just use this one. Yes?
For the for loop, would it be better to start at 0, or is that just pseudocode? Or?
We'll get to that in a second. That is a function of the algorithm.
Okay.
We don't start at 0 for a reason.
Okay.
So any questions on reading the pseudocode? Yes, sir.
Dumb question. When you get to n-1, and then it was going to check again and see, go to n, but it's not in the requirements.
So ask your question one more time, so I'm not sure I understand.
Well, it says I is less than n, but the largest element of the array is n-1. So what happens once it's less than n-1, and it's supposed to check again and see that it can't go to n, but it's going to check?
Are you talking about in the for loop header?
Yep.
So I starts at 1, and we don't see, but it's going to increase by 1 every time. You guys know that. Unless it says otherwise, it'll increase by 1. So I goes from 1 to 2 to 3 to 4 to 5, 6, 7, 8, 9. N is the value of 10. Okay, so when it's 9, we go 2, 10 minus 1, which is 9. So 9 to 9, so that's still good. We're not past there. So we enter that final time. We run through the whole loop. The value of I increases when the loop finishes. So after the loop finishes, I goes from 9 to 10, and then the condition is checked again. At that time, we realize that 10 is past 9, so we stop and we come down here. Does that answer your question? Okay, cool. Okay, so look up all the way at the top. It says, consider the problem of finding the value of the largest element in a list of n numbers. So first thing, notice that we aren't given the size of the array. We aren't given the size of the list of numbers. This is typical for algorithm analysis. We aren't interested in how long it takes to run something at a specific input size. We don't care how long it takes to find the largest number in a list of 10 or 50 or a million numbers. We're always interested in how long it takes in some unknown input size. We want to define the algorithm in terms of an unknown input size n. That makes sense? Okay. So we don't know. There's n numbers. And we want to know the largest value. So that would be like if everyone in here is a value in an array. Maybe let's take your age. And we want to figure out who the oldest person in here is. We would go through and we would run the algorithm to figure out who the oldest person is. All right? We could do it, but we won't. So here's how the algorithm works. The first thing we do, notice we're outside the loop. We set max value equal to a at 0. So this is the same thing as taking whatever the first value in the array is, and we're going to store that. Okay? So how old are you? 21. So we're going to take 21 and we're going to put it inside of max value. Okay? Right now, that is the largest value that we have found so far. The next thing we do is we hit the for loop. So this is where we start the repetitive process. Okay? That is why the for loop starts at 1 and not 0. Because we already know how old the first person is, the largest value. So now we want to come in here and we're going to start the loop. So, start I at 1 and we go to the very last element. If A at I, so this is now the second or position 1 of the array, is larger than the highest value that we found so far, meaning we found a new high value, then our new high value becomes the highest value we found. Okay? So let's go to the next position. How old are you? 28. 28 is larger than 21. So now we have a new max value. 21 is forgotten, and we go back up. I becomes 2, and we check to see if that value is larger. How old are you?
25.
25. Not larger than 28, so we simply skip over this, and go to the next guy. And we proceed all the way through. Okay? At the very end, we simply return max value. Okay? Now, if you look up here at these 3 comments at the top, you'll always see those 3 set of comments in this form of pseudocode. The first tells you what it does. So this algorithm determines the value of the largest element in a given array. And then it'll tell you what it accepts and what it returns. So the input to this is an array, starting at 0 to n minus 1, of real numbers. Output, or the return, is the value of the largest element in the list. So any questions on this algorithm? So now that we know how it works, let's get into the process of taking this and coming up with big O notation. Coming up with its complexity. So the way we do that is by answering a series of questions and going through our own algorithm to break this down. So the first question is, what is the input size? What is the input size? Anybody? Yeah, so it's a list of n numbers. Very good. We've got a list of n numbers. The input size is n. So the next question is, what are the operations? What are the different operations? And this is kind of a question that primes us to get ready to answer the next question. So we're trying to figure out what the basic operation is. And the way we figure out what the basic operation is first identifying what the operations are. So what are the operations of this? Yes? Okay, so we have the comparison method, which is here. Okay. The addition, where's the addition?
Well, it's going to continue to add one out of the loop, as you said.
Okay, good. So we have, we'll take the for loop. We'll put the for loop as 1. We have the comparison here. What else do we have? What other operations do we have going on?
Return.
We have the return statement, good.
Assignment.
Assignment and assignment. So we have 2 assignment statements. We have a for loop. We have a comparison, we have a return. So we really have 1, 2, 3, 4, 5 operations. We good with that? Now, what we want to figure out is which of those operations is the basic operation. And you guys hopefully remember that a basic operation, the basic operation of an algorithm, is the one that contributes most to its total runtime. And so there are some guidelines that I'm going to give you that will help you identify what the basic operation is. Now, I'm sure in this algorithm you can probably pick it up pretty easily. But let me give you these guidelines because this will help you as our algorithms become more complex. So the first thing that you want to do is eliminate any operations that only run once. Eliminate operations that only run once. So let's eliminate operations that only run once. Which lines of code, 1, 2, 3, 4, 5, which ones only run once?
5, 1, 1.
5 and 1, good. By definition, a return statement can only run once. Because it runs and then the method stuff. So I'm going to cross this one out. You guys also said that line of code number 1, the assignment statement that occurs before the loop starts only runs once. That is also correct. It runs once, so we're going to ignore it. Okay. Good so far? All right, so that's your first guideline. Ignore lines of code that only run once. Second guideline. Ignore for loop headers. Okay. So, rules. Number 1. Ignore operations that only run once. Number 2. Ignore for loops. Yes?
I was just wondering why.
I was gonna
try and guess why.
Go ahead, let's see if you can answer.
Is it because the for loop pretty much only occurs one time and then you're inside it occurring?
So, what's the difference? Does anybody know the difference between the way for loop and while loops are run?
Yes.
Anybody use that information to... let me say it this way. While loop headers are not ignored. While loop headers very often are basic operations. So what is the difference in terms of why you think a for loop header would be ignored but a while loop header would not? In terms of how the compiler reacts to a for loop versus a while loop. Go ahead.
With a while loop, the conditions are already set, or like it's while something isn't equal to something. But this seems more arbitrary. Like you have to make sure something is assigned so the computer thinks it's, okay, a bigger thing.
Okay, that's good.